Hey there, functional programming fans. Welcome back to another exciting episode of Purely Functional Data Structures. Last time we started the series by talking about linked lists, and we were particularly interested in how we could create a second list and concatenate those two together in a functional way. Our ultimate goal was to have references to these two original lists and to ensure that those references remained valid even after the concatenation. We accomplish this goal by recursively copying each node from the first list and prepending it onto the second. We could then create a reference to the new list while ensuring that x and y still held the same value that they did at the beginning. We observed that we only need to copy nodes that an imperative programmer would modify in place. Today we'll examine the same principle in a slightly more complex context, looking at the binary search tree. Trees are represented in a similar way to linked lists. We start with a container and we can stuff a piece of data into it. Then we have some number of references from that container to other ones in the tree. Now for a binary search tree, we only need two connections. Using these two connections, we can ensure that items are sorted as they come in by always putting smaller values to the left and bigger ones to the right. Notice how this forms another recursive structure. So if we're looking at any particular node, it doesn't really matter if it's at the top or if it's at the bottom of some larger structure. We can design our algorithms thinking just about one node at a time. Just like with lists, we can even build up structures that share nodes with each other. So if we're looking at this tree through a particular reference, x, then we call the node that x is pointing at the root node. We say that x contains all of the elements from its root node down. So let's think about adding a new element to a tree. Because this is a recursive structure, we only have to think about two situations. Really, we start by thinking out our base case, which is when the tree is empty. If the tree is empty, then we just allocate a new container and put our element into it, and then we create the two empty nodes that this container is going to reference. We may want to add another element now to this tree, even though we know it's not empty. So to start off, we're going to have to examine that root node. And here we can see that our new element is greater than the root, so we're going to have to insert it on the right. But this puts us back in the same situation. Here we are trying to add a new item to a tree. So again, we look at this current root node, and we see that our new element is smaller than it, so we're going to put it on the left. Now, at last, we've come to our base case. We see an empty tree and we know exactly what to do. We build a new node for our new item. Of course, we can't destroy our existing data structure by updating the reference to the left of the 10. So we're going to have to copy that into a new parent node. But of course, we can reuse everything that was to the right of the 10. Now we have the same problem again, because we want to attach that 10 to the 5. We can solve this problem the same way. We just need to copy the 5 to a new node to be the new parent of the new 10. So ultimately, this generalizes the same way that inserting elements into the linked list did. We allocate a new node for the new element, and then we build up all the parts by copying the chain of node that leads to the new one, and we only copy that particular chain of nodes. I've already set up some to-dos in our code base, but first we need to define the types. I mentioned last time that I like to avoid using null wherever possible, so again we will create a specific type to represent an empty tree. This is just an interface with a tag field that we can use to identify that type at runtime. A node that does contain an element will look a lot like the linked list node, but it needs two references to other trees, a left and a right. The binary tree itself is a union between these two interfaces. We'll need some constructors, but empty trees really can all share the same instance. So we just need to declare a constant instance and expose it with just a normal old variable. Creating a tree from an element will give us a different result each time, so we need a function to build up a node from an item, a left tree, and a right tree. Of course, these two child trees can default to be empty. I love using the spread operator in unit tests to check for equality. It's easy to expect our set to spread out to an array, and then expect that array to be equal to some value like this. But to get this working, we'll need to extend the iterable interface. These interfaces now expect the symbol.iterator field to be a generator function. The star at the beginning signals that this is a generator rather than an ordinary function. And the body would yield the values of its object in order, but the empty tree doesn't have any values, so it can just have an empty body. And we can see that now our test is passing. When creating a generator for a non-empty tree, we first need to yield all the values less than the current one, then the item itself, and then finally all the values larger than it. And that way the resulting array will be sorted. We know that all values less than the item are stored in the left tree, so we can start by giving all the values from the tree's generator. The yield star keyword lets us do just that. Next, we need to yield our current value, and then finally we give control over to the right tree's generator to get all the larger elements. Let's refactor our test to use a non-empty tree. Awesome, that's passing too. Now, we'll want to be able to check whether our tree contains any particular element, so we'll create a function that has the right type signature. To test it, we can create a tree with a few elements and assert that it does contain those elements. We should check that it doesn't contain an extra one too. So whenever we're implementing recursive functions, we want to think in terms of possible situations. For example, maybe the tree is empty. If so, we know that the tree doesn't contain the element. On the flip side, maybe the current element is the one we're looking for. Well, if that's the case, then we can return true. If the current tree is not empty, but the current element doesn't equal item, then we can check if item is less than the current element. If so, we just need to search the left tree. Now, the only scenario that hasn't been ruled out is when the item is greater than the current one. So if that's the case, we just need to search the right-hand tree. We can adopt the same workflow to implement our insert function. First, we create a stub with the right type signature. Then we write a test that creates a few trees that all build off each other. This way we know there's some node sharing going on. And then we can assert that none of those references have changed during the process. First should only contain 5, second should only contain 4 and 5, and finally third should contain 4, 5, and 6. It's worth checking too that we can insert the same element twice without affecting the results. Just like before, we're going to think in terms of possible situations, starting with the base case, which is when self is empty. Here, we just need to create a new tree with the item and with empty left and right fields. We might also be trying to insert an element that's equal to the current one. In that case, the value is already in the tree, so we don't need to change anything. Now we just need to decide whether to insert it into the left tree or the right tree. We can make that decision by checking whether the item is less than the current element. If so, we should go to the left. Otherwise, it goes into the right. See how in these last two branches, first we create the new child tree, either for the left or the right, and then we pass that result into create. That's how we ensure that all the nodes up to the insertion point get copied, because except for when we return self unchanged, we always end up passing the current element to create at the end of our recursive call. We should be following these references all the way down to the point where we find a completely empty node. Then we create a new tree and step back up the call stack, creating more nodes as we do. One thing to consider is that this algorithm is not tail recursive, because as we walk back up the call stack, we still have more work to do at each step. We still have to create the new node. Usually we like tail recursive functions because many compilers can optimize those function calls without pushing new frames onto the stack. So they take out the function call itself, so that the stack doesn't need to get filled up with call frames. Without tail recursiveness, our function can only make recursive calls until those stack frames eat up all the stack space. Interestingly, Node currently does not remove tail recursive calls, so we don't get any benefit there either way with Node. Just for fun, let's try to implement this function without using recursion. First, we can copy the type signature and give it a new name, and then we can duplicate the test. To approach this implementation, we can really mirror what the recursion was doing for us behind the scenes. We're looking for the right spot to put a new element, and those function calls created a queue for us that kept track of all the parents that we needed to copy. We can just manage a queue like that manually. Now we know that queue contains all the parents that led up to our new entry. So first, let's create that new node. Now we can iterate through the queue, copy each parent, assign our previous node to either the left or the right, and finally update our node reference. We might be doing a lot of things here that my functional elslint plugin doesn't like, but our test is still passing. Even though we have some mutable local variables, from the outside our function still preserves the immutability of the entire data structure. And that's what we really care about. Thanks for watching, everybody. Feel free to leave any questions or thoughts you might have in the comments below, and check the video description for any relevant GitHub links.